right, so Calculus 1 students, what we're going to do now is look at the third part of the notes for 2.2, and we're going to focus a lot on what happens to a function around a asymptote. Okay, so to begin with, we want to go ahead and remind ourselves of what a rational function is. Okay, so let's go over that a little bit. So in general, a rational function is a ratio of polynomials. The denominator contains a polynomial of a degree of at least 1. And what that means is you have to have x to the first, but that exponent has to be greater than or equal to 1. Okay, it can't just be a whole number. Okay, so some examples of rational functions. Let's just write down a couple. Okay, so one example might be something like 3x plus 2 in the numerator. That's a polynomial over x squared minus 2x plus 1. That's also a polynomial. So that's a ratio of polynomials. So we're going to be looking at fractional functions that are ratios of polynomials. Another one might be something like you just have x minus 2 in the denominator. That's okay because you have a power of 1 or higher on the x. Same thing here. You could just have something like, you could even just have a number in the top. It's okay to have a number in the top. So the thing on these rational functions is typically they're undefined somewhere. Not always, but a lot of times there are places that make the denominator undefined, and that's where you end up getting a vertical asymptote. So what I'm saying here is a vertical asymptote occurs on a rational function when the reduced form, and I think that's pretty important. The has to be reduced where that's undefined, right? And we'll talk about what happens on that. I'm going to mention one thing here. If you had something like this rational function, x minus 1 over x squared minus 1, well, it turns out that you could factor the denominator, and you would have x plus 1 times x minus 1, and that would cancel that out. So the leftover vertical asymptote would be there. Okay, so this function's undefined at -1, so you'd have a vertical asymptote at x equals -1, but you wouldn't have one at x equals 1. You would have what we call a hole. So we'll kind of look at some situations like that in a few minutes. So the idea is the vertical asymptotes where the reduced form is undefined. So that's what we mean by that then. Okay, so let's go ahead and look at this example. We're going to go ahead and put this in the graphing calculator. So you want to put this in, so we just go 1 divided by, and it's important that you have the, the x minus 2 in a set of parentheses. If you don't have that, it's not going to evaluate the arithmetic correctly and then going to make the right graph. Okay, so let's do that in a standard window. So you can go zoom 6 to get that in a standard window. That's what your rational function looks like then. Let's go to our table and let's construct a graph of this. First thing you're going to notice is we have an error at 2. That's because this function is undefined at x equals 2. Okay, so just go ahead and start by drawing a vertical line through x equals 2. And just get a few other points. We'll just look and find a couple other points. Like here's a point 3,1. All right, here's a point 4.5, like that. What you're going to find is the graph is going to kind of level off towards the x-axis. It's going to swing up towards the vertical asymptote and go towards infinity. Okay, another good point is 1, -1. And let's use 0 and -0.5. So what you're going to find on this is this graph's going to kind of do this thing. Level off towards the x-axis. You're going to have what you call a horizontal asymptote. All right, so we want to get that established. And then we're going to trace out this table of values like we've done before. Okay, so once we get the graph, let's go ahead, and what we're interested in is what's happening to this function at x equals 2. All right, so we're going to be doing the limits around x equals 2. So we're going to do this. We're going to trace values. So let's start by getting a number that's below 2, like 1.9. So we're going to trace 1.9, and then we'll just record as we do this then. Okay, so that gives about -10. All right, now let's do it again. 1.99, closing in closer to 2 from the left. That's -100. One more time, 1.999, that's even closer still. That's -1,000. Okay, so what's happening here? What's happening? As you get closer to 2 from the left, what's happening? Yeah, that's getting smaller and smaller, so it appears that it's going towards -infinity. So if you look at the graph, that makes perfectly good sense, basically on what we've been talking about. If you come from the left, that thing's going to go to infinity. So this left-hand limit, we're going to say that limit approaches -infinity as x approaches 2 from the left-hand side. All right, now let's do like kind of close in from the right. So we'll do kind of the same thing. Trace at 2.1 and record. That gives a value of 10. Get a little closer to 2 from the right-hand side. That'll give 100. Get closer still. And that will give 1,000. It's got the same pattern. Okay, so the idea is what's happening as we get close to 2? What's going on? This number is getting bigger, so it means that's going to infinity. So we would say that right-hand limit from the graph, you can tell the closer you get to 2, the graph just swings up and goes to positive infinity. All right, now the two-sided limit, what do you think? It's going to different places, so what do we know? Okay, so that does not exist. That's the idea. So that will happen anytime you have a vertical asymptote. That's always going to happen too. The graph is either going to go to infinity or -infinity, right? There are times when the two-sided limit will exist, and we'll certainly see that here in just a minute. I'm going to open up this Geogebra app and see what this is. This is real simple. This is just something that I want to show you. Like on this graph right here, the vertical asymptotes are where the function's undefined. This function's undefined at 1, and this function's undefined at 2. So what you're going to notice on this is, like I said, around a vertical asymptote, the graph either goes to infinity, like it does there, or it might go to -infinity, which it does in between there. So it just sort of depends on how the function is written. I want to show you this. The way that you can do this is you can kind of slide these things, and it'll slide the asymptotes a little bit. So now we have an asymptote at -4 because we're undefined there. Now we have an asymptote at x minus 2. I don't know if this will allow me to change this. It might. If I put like a negative here, let's see if this does anything on here. I don't know if it's going to do that or not. There we go. Okay. So I put a negative there. And that just, you still around the asymptotes are either going to infinity or you're going to -infinity. Now, the direction they're going depends a lot on what's going on in the numerator, whether the ratio of the numerator and denominator are negative or positive is what that turns out to be. Okay. So again, you can kind of play with this a little bit, and you can see how the asymptotes change. That's just where the rational functions undefined. Okay, I like those applets. They kind of are good ways to make connections, I think. All right, so let's move to the next page, and what we'll look at on this, continuing this discussion, what this is saying is a vertical line, x equals a is a vertical asymptote for the graph if f of x approaches infinity or -infinity as x approaches a from the left or right. So that's what I'm saying is the graph's always going to approach infinity or -infinity around a vertical asymptote. So that means it's going to increase upwards or decrease downwards without bound, so it's going to go to infinity. Okay, so let's do the same thing on the next problem. Let's work with the graphing calculator a little bit and get this thing put in. You're going to, again, kind of see how the second power affects things a little bit on this. So first of all, what happens on this problem is if you look at the vertical asymptote, again, you look at where the reduced form's undefined, so you can do this in your head. X plus 3, if you set that equals 0 and solve that equation, that means you get a vertical asymptote at x equals -3. So the first thing I want you to do is just draw your vertical asymptote at x equals -3. Like that. The rest of this we're going to do on the graphing calculator because we're trying to get an understanding of how this works. And then eventually we're just going to get away where we don't need to use calculator anyway. It's a real simple thing you can do to figure this out. And we'll get to that in a little bit here. Okay, so again, what you want to do is numerator in parentheses, that's necessary, denominator in parentheses. So x plus 3, close parentheses to the second power. So that's how you input that into your graphing calculator. What I'll have you do next is just graph in a standard window. Zoom 6 is a good way to start. We see everything that we basically need to see there. Okay, and like we've been doing, we're going to trace values. So what we're interested in this problem, we're going to go ahead and construct a graph. And let's go ahead and just go table of values, second graph. And let's find some good points on here just to start with and get a pretty good graph. This is what I want you to do. If I want you to do a graph, I want you to have an accurate graph. So you can make it as accurate as you want to with a graphing calculator. So we have a point -4, -5. I'm going to use that. I've got, what else I got? I got -2, -3. Okay, and then you can just kind of sketch these things. It doesn't have to be perfect. Here's -5, -1.5. And then you can just sketch the shape. It's going to go like that according to the graphing calculator. That's good enough. Get a few other points. Here's -1, -0.5. Here's 1, 0. Like that. And then from there on out, it looks like it's above the x-axis. You can tell these are positive numbers. So it's, excuse me, kind of doing something like this. And it's just barely above the x-axis. But it looks like it's just going to get, as you go further and further out, it looks like that number, that y value is getting close to 0 the further out you go there. All right, so that's a good graph. Now we're going to do some tracing and kind of see what's going on, okay? All right, I had to pause the video because I was afraid the cat dragged something in. I record these videos from home, and every now and then the cat will do something bad. She likes to bring in critters. Her name is Bigfoot, and she's a terror. All right, so let's trace these things out then, like we've been doing. So what we're going to do is this. Let's start tracing values. All you got to do is type trace once usually. So -3.1 is going to give -410. So you're way down below. -3.01, closing into the asymptote closer. It's getting smaller. -40,100. So hopefully you're getting the point here. -3.001. Oh, look at this. Oh God, what is that? 4 million. That's huge. Or no, it's small. Okay, so we got that. All right, now let's close in from the other side and see what we got here. Let's go with -2.9. And that'll give -390. -2.99. That gives this 39,900. And closer still, -2.999 will give this. That's -3,999,000. Okay, so that's the idea. So the idea on this is once you get those things traced out, if you're coming from the left, what's happening to this number? It's getting smaller. So it looks like that's going towards -infinity. That's clearly what the graph is saying. As you close into -4 or -3 from the left, that thing's going to -infinity. Okay, what's happening on this is if you close in from the right, those numbers are getting smaller and smaller, so that's going to a -infinity. So this is representing the right-hand limit going to positive infinity. Okay, so we would make our conclusions like this. The left-hand limit goes to -infinity. Right-hand limit also goes to -infinity. Therefore, the two-sided limit also goes to negative infinity. So the graphing calculator can trace out values, and it should make it real clear how the graph is behaving, okay? So that's kind of what you do graphically. What we're going to try to do on this a little bit, though, is begin to look at what we can do without graphing, because we don't want to have to go through this every time. You don't want to have to put this in the calculator. You want to be able to look at the function, do a quick calculation, and figure it out. So the idea with this is this. If you're going to evaluate a left-hand limit around a vertical asymptote, pick a number to the left of the vertical asymptote, a real small number, and plug it in the function. And then instead of doing this, just calculate it. You really don't have to calculate. You just got to figure out if it's negative or positive. To evaluate a right-hand limit, pick a number to the right and evaluate. All right, so that's what we're going to do on the next page. So let's go on to the next page. All right. All right, so the way you want to look at this now is, first of all, this only works for a vertical asymptote. So don't do this unless you have a vertical asymptote. Okay, you have to establish that I'm asking you a limit around a vertical asymptote. So if you look at this first row, this function clearly is undefined at 9. Okay, so what you do is you make the conclusion that, yeah, we have a vertical asymptote at -9. So we have a vertical asymptote at x equals 9. That means that we can do this, and I'm asking you for the limit at the vertical asymptote. If I wasn't asking you for the limit at the vertical asymptote, you wouldn't use this approach. So here's what we do. This is a left-hand limit, so we're going to pick a number smaller than 9. Okay, let's pick like 8.9. Okay, just close to it. All right, and plug it in. So what we're going to do is where we see x, we're going to put in 8.9. So we got 8.9 plus 4 over 8.9 minus 9. Now, you do not have to get out your calculator, guys, okay? The thing is, the numerator is positive. The denominator is negative. So a positive divided by a negative is a negative. Therefore, we conclude that that's going to negative infinity. That's all you got to do, all right? You don't have to do a calculator. You can do that super fast, okay? Next one is a, excuse me. All right, kind of woke up with a cold this morning. So next thing we want to do is, this is a right-hand limit. So let me kind of show you what you're going to do here. Same idea. It's a right-hand limit. Use a number that is a little bit greater than 9. So let's use like about 9.1 because it's a right-hand limit. So we're going to plug in and we'll get 9.1 plus 4 over 9.1 minus 9. Okay, the numerator is positive. The denominator is positive. What's the result? Positive. Therefore, the answer to that limit is positive infinity. That's it. That's all you got to do. Now, how about the two-sided? Well, we've done this enough by now. They're going to different places. One's going down, the other one's going up. So that one does not exist. And that's it, okay? Now, just one more time on this. It is always kind of worth seeing why this works the way it is. You don't need to draw this graph, but if you put this in, you would have x plus 4 divided by x minus 9. I'll just do a graph of this in a standard window, and then visually, we should be able to see what we found, okay? Kind of hard to see how the right-hand limit's going on that, so I might need to expand that out. One thing you can always do is zoom out on these. So if I go to option 3 and just zoom out, well, now you can see pretty clearly. Negative infinity, right goes to infinity. So that's it, okay? All right, so I'll do one more on here. All right, so this one is a left-hand limit. So we want to use a number smaller than 3. So let's use like 2.9. You want to get close to it. You could use 2 and it'd probably be fine, but I'd recommend just use a decimal. So let's do 2.9 over 2.9 minus 3 to the second power. So what you get is a positive numerator, and see 2.9 minus 3 is negative, but when you square it, it becomes positive. So you end up with a positive over a positive. Therefore, that's going to go to positive infinity. Okay, that's all you're trying to do is see if it's positive or negative. That's it. So the squaring thing on there, that's what made the denominator go to a positive. All right, next one's right-hand limit. So we want to use something a little bigger than 3. Let's use 3.1. So we'd have 3.1 over 3.1 minus 3 to the second. That's positive. Again, that's positive. See, anytime you square anything, you're going to get a positive number unless you end up having 0. Okay, so that's positive. Therefore, that would go also to positive infinity. Okay, and that's the idea. All right, so therefore, what's the two-sided limit? They both go to infinity, therefore that is infinity. Okay, and that's how that goes. And again, you don't have to do this every time you do these problems, but I think it's worth it as you're learning this. If I put this in, I have x divided by x minus 3. And the second power made a difference on the way this looks. So now if I zoom 6, you can see that, well, clearly that's what the results showed. Okay? All right, so that's it. Now, just go ahead and pause the video. I want you to do the next 2 problems without a calculator. You're more than welcome to verify on the calculator to see if you're getting this right. Okay? Okay, so let's check and let's see if you got the right answer. I went ahead and put the graphs up too, just to kind of verify on here. It's all arithmetic. This one is a left-hand limit. So therefore, I used 4.9, a number smaller than 5. So I do 1 over 4.9 minus 5. Positive numerator, negative denominator makes a negative. Therefore, it's negative infinity. You can see by my graph, it's going to negative infinity around that asymptote. Right-hand limit, use like 5.1. So you'd have 1 over 5.1 minus 5. That's positive over positive. Therefore, it goes to positive infinity. See on my graph, I'm going from the right of the vertical asymptote, it clearly goes to infinity, right? So therefore, the two-sided limit does not exist. They're going to different places. Next one, you have to be kind of careful about that cube. So this goes like this. This is a left-hand limit. I used a number to the left of -1, like -1.1. Plug it in. I get a negative numerator. Now, watch this carefully if you didn't get this. I can see how students can mess up on this. When you plug that in, you have a negative number to the third power, which just means negative times negative times negative, which is negative. So you end up getting negative over negative, therefore it goes to positive infinity. Look at my graph, that verifies that clearly. Right-hand limit, I used negative 0.9, that would be a number to the right of -1. Plug it in, I got negative over positive, which is a negative, okay? So that went to negative infinity, therefore the two-sided limit does not exist, okay? That's what you do. So if you know you're doing a limit at a vertical asymptote, that's a case that you learn to look for, then that's what you do without graphing. You can almost do that in your head. And for higher math, I would recommend that you're able to do that. I can think of situations in higher math when you need to kind of quickly know what's going on around a vertical asymptote. You don't want to waste time. You want to mostly just do it in your head, okay? Okay, moving on to next thing we're going to talk about is what we mean by deleted point or a hole if you have what's called a 0 over 0 form of the limit. So to begin with, what we want to do on this problem is we want to factor and simplify first. So you want to go ahead and just factor the numerator and denominator. All right, so let's go ahead and do that. We need to do that first of all to figure out the asymptotes. And remember, asymptotes occur where the reduced form is undefined, the key being reduced. So the numerator, you would draw 2 parentheses. You have x and x. 2 numbers that multiply to give 6. You're either going to use 6 or 1 and 3 and 2. 3 and 2 is better. If you want 3 and 2 to add up to -1, you have to have a negative and a positive. if you're shaky on factoring, one of the things you need to do now is review it, okay? I'm likely to put something up on My Math Lab or probably in the next week's module, something that if you feel like you need to review factoring, then do that, because it's a big deal in calculus. All right, this is a difference of two squares. All right, so you do x times x to get x squared. You do 3 times 3. All right, you don't have a middle term, so if you want it to cancel, you do plus and minus. Okay, so that's how that goes. All right, this one cancels out. So the place where it cancels out is not a vertical asymptote, it's just a hole. It would just be like a bubble in the graph. But the place that didn't cancel out would be where your vertical asymptote is. So what you're going to have is, you do this in your head, a vertical asymptote is going to occur at where this thing is. All right, so that is x equals -3 is where your vertical asymptote is going to be then. All right. All right, the hole is going to occur at x equals 3, and I'll show you kind of how that shows up on the calculator. So it's always the one that cancels that gives you a hole in the graph. All right. Now what we're going to do on this problem is we're going to graph this on the calculator, and we're going to put in the original function. So you can either watch this or you can do this with me. It's always a good idea to do the graphing with me on here just to make sure you're comfortable where the buttons are and everything. So we're going to do x squared minus x minus 6 divided by x squared minus 9, and we'll do that in the standard window. So we're going to do a zoom 6, and we're going to get this. Now what I'm going to do on here is, we know we have a vertical asymptote at x equals -3. And let me zoom on this a little bit so I can see what I'm doing. Okay, so you want to go ahead and draw your vertical asymptote at x equals -3. And I'll talk about what happens on the hole here in just a minute. Okay, so let's do our table. Let's get some accurate points, just as many as we can. I try to look for whole numbers if there are any. Sometimes there aren't any. We may not find anything on this one. So just get estimate a couple of points. Here's, let's see, here's -2, 0. There's a couple of them around here. So let's use some of these. There's -4, 2. There's -2, 0. -5, 1.5. And so forth. Okay, that's probably good enough. Here's 1.75. So just something kind of like that. But I want some accuracy on graphs, and then from here we can just kind of sketch it in. So you can pretty clearly see how this part of the graph's going. It levels off towards the x-axis. Around here it looks like it goes kind of like this. And that thing is going to level off at 1. It's not going to go to infinity. There's a reason that I know that. It has to do with what's called the horizontal asymptote. All right, so that's a reasonably good graph there. Now, what's going to happen on this is we have a hole at 3. So you want to go to your graph, just kind of erase that, and just somewhere in there put a little bubble there to represent that hole. Okay, so what you have is vertical asymptote here, and then you have the hole there. Okay, sometimes you'll hear this called a deleted point. I usually just call it a hole. All right. So I'm going to show you how you would do these limits. It's pretty clear you could do these limits in your head good enough, certainly. So the idea on this would be this. And again, see, notice we're doing this around an asymptote. All right. So what we're going to do here is, the first thing you do is, if you plugged in the number, we're going to try to get away from doing the graph. If you plugged in the number on this, and you want to write this down because this is how you always want to start a limit algebraically, just plug into the original. You would have -3 squared minus -3 minus 6 all over -3 to the second minus 9. So we'll have 9 plus 3 minus 6. And then the denominator, I'm going to have negative 3 to the second minus 9. Okay, so it looks like you get 6 over 0. All right. So that, doesn't necessarily mean the limit's not going to exist. We know that's undefined when you plug that in. So the way that you would want to do this is you would want to go ahead and simplify this. So we would have the limit as x goes to negative 3 from the left. Like we did, we factored. So we have x minus 3, x plus 2, all over x plus 3, x minus 3. Those things cancel out. And then what we do is we just reevaluate the limit. So now you plug in. So what you're going to end up having on here is you're going to have negative 3 plus 2 there. Okay, then we have plug in here, you're going to have negative 3 plus 3. So again, you get this negative 1 over 0 thing. All right, now again, that doesn't mean that the limit's not going to exist. The thing that you have to understand is you're being asked for a limit at a vertical asymptote. So what that means is you're going to do test points. So this is a left-hand limit. So what you would do is the result of this is you got x plus 2 over x plus 3. After you simplified it, you got that. Use a test point that's to the left of negative 3. So let's use negative 3.1 and do what we previously did. And since we know that this is an asymptote, we know we're going to get an answer of either negative or positive infinity. Okay, so this is going to be a negative numerator over a negative denominator. Therefore, that's plus. Therefore, the answer is positive infinity. Okay, that's how you do that. All right, so what you do really is, since you know I'm asking you for a limit around a vertical asymptote, it's all about doing test points. That's the idea. And we're going to do the same thing on the next one. All right, so this one we're really doing the limit as x approaches negative 3 from the right. And let's just do the final form. You could do this in either the original or factored form. Certainly easier this way. Right? This is a right-hand limit. Therefore, use a number barely to the right of negative 3. Let's use negative 2.9. Okay, so then plug in. So you'll have negative 2.9 plus 2 over negative 2.9 plus 3. So that's going to be a negative over a positive. That's a negative. Therefore, the answer is negative infinity. Okay, so that's how that goes. The graph certainly verifies that. But that's how you would do that without graphing, is do the factoring, verify that you have a vertical asymptote, verify that you have a hole. Okay, and since I'm asking for the limit around the vertical asymptote, that's why you use test points. Okay, that's the whole idea. All right. So then from there, of course, we know that this one does not exist. Right? And again, when you're doing homework and stuff, don't always graph. I mean, you want to try to do a lot of these things independently of graphing, but then verify graphically. Unless you have to graph, don't graph. Seriously, that's what I want you to do. Use it as a verification tool. Okay, so that will finish up that this part of the video. The next part of the video, I'll do one more part. We'll talk about a limit at infinity. So that's the end of that. Hope you enjoyed this entertaining video and it helps you understand how to deal with limits around vertical asymptotes. Good luck.